this particular talk is about our love for interfaces in Go, and we're going to use one of the first big projects in Go that we did at Cloud, which was a rate limiter called Sphinx. So before we go into why we love interfaces and how they make everything better, I want to give some sense of what Sphinx is. Sphinx, like I said, is an HTTP rate limiter. It exists completely outside of our applications and sits on top of every API request that comes into Cloud. It's really configurable in terms of you can create a lot of different limits and you can select what requests apply to which limits and how you construct keys so that you can use multiple axes or compound axes to limit users or IP addresses on. One of the things that we had to do was to also build a leaky bucket library, which the Sphinx rate limiter is built on top of, and it's also in code. We found that benchmarks were really awesome because from the very beginning we knew how much time each component took, and we were able to get, for even complex requests, sub 15 millisecond latencies on top of our existing infrastructure, which is important since every request was hitting Sphinx, sometimes with lots of large payloads that we had to call. So I want to do one more thing before we dive into the actual construction of Sphinx from the bottom up, and that is, what is a limit? I'm not sure if everybody has used rate limiters before, but in general you define the maximum number of requests that you can make per interval. We don't do any traffic shaping. We can have more questions about this. And then you also then describe a matchup based on request properties of which particular limits a request should be tested against. And like I said before, you could decide that, I want to create a limit that is unique to every IP that I get requests from, or I want to create a compound key where every IP for every user has a given limit. So, any questions before we dive into interfaces? Yeah?
You might get to this later, but I'm curious what procedure you use to do the rate limiting, in as much as is it arriving sort of in chunks or is spaced?
Yeah, so great question. So there's two major ways of doing rate limiting. One is that, let's say, let me take an example. I set an interval of 10 seconds and I want to set 200 requests as the limit. We do not do traffic shaping, which means that the request will always be equally spaced in the 10 seconds. That makes it very hard for developers using your API to know what is going on, because a request might fail and the other one might go through, or you have to queue every request and hold on all the connections before you let it through. So for the kinds of throughput that we're looking at, and most of the other implementations out in the wild never do traffic shaping because of those reasons. Traffic shaping does become important at much more lower levels when you're dealing with packets. For HTTP requests, it seems like it's not as useful.
Okay, so I guess now I'll talk about kind of how we use interfaces to make building Sphinx really easy. Sort of like what benefits it had from a software engineering perspective. So first, for those of you who aren't familiar with interfaces in Go, basically an interface defines a list of methods, and then any struct that has those methods implements that interface. So like, as an example, you might have a struct called IP limit key, which implements our limit key interface because it has a key and a type function. So like, this is like how we implement different ways to rate limit people. So you can rate limit people by IP or header or path or any sort of thing like that. There's just different implementations of the same interface. So how did interfaces help us in Go, or help us in Sphinx? So they came with benefits for collaboration, testing, as well as allowing swappable behavior. So let's jump into like collaboration. So when you're first starting on a project, the common questions you ask are like, who works on what and where do I start? And that can often be a hard problem with a very large project. All these different components have different dependencies on each other, so like you have to have some sort of like hierarchy about where you work on them in. Unless you use interfaces, and then you can define your interfaces for your different components ahead of time. And then you're not dependent on other components in terms of like what order you build interfaces in. So that allows flexibility, it allows you to not be blocked by your teammates. Just like across the board, a better way to do large projects. So as an example here, for Sphinx, we made this like rate limiter interface was like the first thing that we made, which is like the core of Sphinx. Like Sphinx is rate limiter, and it has this rate limiter interface that takes in a request and returns information about whether or not that request is limited, and if so, why it was limited and how it was limited. And then anything that depends on this interface can provide mock implementations of the interface, or like use their own mock implementations or whatever they want to specify arbitrary behavior, as well as doing like assertions on results of, or like expected, so setting up arbitrary behavior for what the limit does, as well as setting expectations for what the limit is going to receive. If that makes sense. We're not going to go too much in depth into this code unless people want to. It uses like lots of third-party libraries, so like, yeah.
Yeah, so before I move on, so any questions? So I know one of the things is like, one of the things that we were very excited about using interfaces in Go was like, we all learn about like using interfaces in like context of school, but you never, it's always too much overhead to actually use it in real projects. But in one of our first projects in Go, we found that since interfaces were so lightweight and we could easily change them, and it would, the compiler would tell you what other things you need to change. It was really low cost to add these interfaces and iterate. So I guess to give you some context, over the first week we changed the interfaces and stepped on each other's toes all the time. But after that we were able to build different parts of Sphinx and even build the top layer before we had any other parts on it, which was the HTTP part, which we were very excited about in the beginning. And so we talked about the mock-based interfaces, but there are other ways that we found testing was great when specifically focusing on interfaces for our leaky bucket library. In general, what we really wanted to do was to have at least two implementations, which was an in-memory implementation and a Redis implementation. So what that means is that if we had multiple servers running, we wanted to compute in one place what limits were being set. But as we continued development, we wanted those implementations to stay in sync, not just in terms of their interface, but also their behavior. So and that usually becomes hard. And also we were finding different bugs in the implementation because they were being used some of them were being used in staging, others were being used for tests. And so we wanted to work on it in a way so that bugs found in one interface were automatically always tested for all implementations. So what we decided to do for that was write the tests on the interface as opposed to on the implementation. And that meant that within that library, all implementations run the same tests, or they have to explicitly state that they are skipping a test by re-implementing a different, an empty version of it. So this is a basic interface in Leaky Bucket. It is a storage, and you can create a name expirable key. So you basically have a total number, which over time you can increment, and it expires after a certain time. So let's look at the test that we wrote for this interface. So we don't have any implementations yet. And what this test does is, so the code in the middle, what it does is it creates a bucket and then checks that the input parameters that we sent, which in this case is 100 and time.minute, were actually the ones that were returned as the properties of the bucket we got back. So this is an example test. And what we are doing is that we are taking an implementation of storage as the input and returning a function to run the test on it. And so basically there is a main function that returns a lot of these tests that are the base tests that every implementation can run. So for example, the two implementations that I talked about in memory and Redis actually need to be instantiated in very different ways. So you can't really just run the test on them. But as you can see, the way by returning a function that is test given instantiation of each of the implementations, all we have to do is, so for example, on the top block, the memory implementation is instantiated just by saying new, whereas the Redis implementation needs Redis URL to create a Redis. And then they both run the same test, so we know that the behaviors are the same. We have lots of tests in the library around race conditions and kind of like edge cases on the deep market algorithm that are tested on both instances. And we know that certain tests fail on a particular instance and they have to explicitly override those. So any questions about testing or these implementations?
So another benefit we got from interfaces, so basically when we talked about different implementations of the same interface with the same behavior, but different like backend structures. You can also do things that implement the same interface with different behavior. We got a lot of benefit from that as well. So we wanted to be able to change behavior of our rate limiter just by changing our configuration. So the way that we did this is anybody, making sure the limits that we'd set were reasonable, like we weren't having partners hitting our limits all the time. And that was again swappable with just like a single config line. So that's pretty easy. Any questions about that, I guess?
Yeah, so one of the other things that happened as we continued building the project is that new people getting onto the project required a lot of context around what were all the things that happened, that were happening in the pipeline and what was going on. But what we wanted was for people to be able to contribute new matchers and keys so matchers are basically what property do I pass off the request and make decisions based on, and then what properties can I use to create keys. And this could be like request paths, params, IP address, headers, and we wanted people to contribute these over time. And we struggled a lot with trying to figure out what is the best way to do plugins in Go, and that's an active discussion topic that we've been part of in lots of different discussion spaces. But for now, the solution that we came up does require recompiles. However, we use some of the interfaces that we already built to provide easy ways to add things, test them, know that the entire system works and behaves in the right way without understanding all different parts of strings. And so I want to give an example by using the matches, which basically decides whether a particular limit will be applied to an incoming request or not. And so it's pretty straightforward. The matcher interface just takes in a request and returns true or false. And the only thing that the thing that we required was to also every matcher has to implement a matcher factory, which is a Java-esque name, but it helped us to not predefine configuration for these. So each matcher can define what configuration they expect in our YAML-based or dictionary-based configuration file. And it returns, so we have two functions there, a type, which returns a string, which basically is the YAML field that we parse, and then find, using reflection, which ones of these matchers should be called. And the create, which actually we just pass in a block of unparsed YAML to them, or the dictionary object, and they are responsible for parsing. And so the bottom half is basically the example of the path matcher, which is just a simple, like it takes in an array of regular expressions and sees if the path matches any of them. And you can see that it defines its own structure, and so the create function actually parses that into the YAML structure, and we call the create functions for every matcher when Sphinx first loads up, before starting to forward any requests, so that we know that all of the matchers will load up correctly. So what this helped us, and this also really helps in tests. So if you are adding new matchers or new features to Sphinx, They are tested completely with requests and just the loading part and just whether they need to succeed or fail, without you having to understand like all the different segments that happen in actual code paths. Um, cool. So, any questions before we have one last thing that we found?
So this last thing was probably my favorite use of interfaces in Sphinx. So again, we talked about the HTTP handler interface, which is part of the net HTTP library. So we got to the point where like, okay, like Sphinx is really cool. Now what we really want is dynamic configuration reload, so we can change the config without taking on the server. So there's this like top level daemon struct in Sphinx that just like continuously running daemon that starts the server and does like all the instant like configuration loading and stuff like that. So this daemon has a handler field on it that is the HTTP handler that we saw earlier, the like logger or limiter, depending on what the config has. And the way that the daemon worked originally was it would just call listen and serve with the handler field of the daemon from its own start method. So we were able to add trivially add configuration reload by making the daemon implement the HTTP handler interface by adding a serve HTTP method that just called the serve HTTP method of its handler and then changing the start method to start a server with the daemon instead of with the daemon's handler. And then you just need to call load config on the daemon a second or third time, which you can do from Sync Hub. And this works because the old handler is like no longer on the daemon, so all new requests go to the new handler, but any requests currently that were sent to the old handler are going to finish before it gets garbage collected. So it's like trivial configuration reload that worked perfectly. Yeah, questions?
So it looks like that Sphinx is like, it should run as a daemon on a server, not. How did you choose to do that rather than having it be a package that you could import and use in your library?
Yeah, so the question was like, why is Sphinx a daemon and not a package? So Sphinx is actually a collection of sub-packages, and there's like a main function that imports some amount of sub-packages to load it, so it's both.
So you intended it to be used both as each sub-package individually and as the main
So,
package?
yeah, as in, there's a very clear answer for why we decided to build it as an independent service rather than build it as library, because we write like, our services are written in multiple languages. Some of them are in Node, some of them in Python, some of them are in Go. We did not want to implement all of this in every language. Also, it's really hard to test what request latencies it would add if it was part of a bundled kind of service that did many other things. We are a big fan of having our services completely separated. So Sphinx, for example, doesn't do any advanced proxying. It can only proxy to one backend because there are many other services that do that very well. However, we did try using HA proxy and Nginx and using their rate limiting, and they were not configurable enough. They did not do advanced request parsing or do multiple parameters. So those are the features that we wanted to build. Yeah.
When you're doing request counting into individual buckets, are you doing that synchronously? Are you writing that synchronously?
So in memory, yes. So there's a lot, like in memory we use, so the in-memory implementation, yeah, it's not thread safe. And however, in Redis, we use a multi-exec block. And also, I think we use a procedure to run the
So it's
increment.
atomic Redis.
Yeah. So you basically can write a combination of steps that Redis will run atomically.
Okay, so then you don't have to worry about the transitions between time blocks.
Yes, so yeah, this is one of the things that, we found out bugs in this because there were certain things that the in-memory implementation made very easily visible that it would have been hard to find in Redis, but since we had already had tests on the expire edges, we did find those issues. In Redis, those issues are solved by setting the expire properties properly, And so if you look at the Redis implementation, there is importance in at what point you set the expire field so that you get the right behavior for buckets that don't get hit again until the very end of when they're going to expire.
How big of a chunk of your, I think it's like 15 milliseconds in your benchmarks. How big a chunk of that is 15 milliseconds?
Sorry, can you please repeat that question?
How big a chunk of the 15 millisecond performance that you guys were measuring is actually doing the right?
Oh yeah, I do not have the numbers in my head right now, but there are, if you run make bench on the repo, it gives you comparisons between the Redis backend and the in-memory backend, which is going to be exactly the number that you're looking for. And it was a significant number, the difference between just using things in memory and doing a network round trip, but it was something also that was very important for us.
It was like low enough that it didn't matter for us.
Yeah, and it was low enough compared to the time our services actually take to respond. So the backend server took a lot more time than the overhead of the Redis back trip.